So thermodynamic relations, last time we talked about equations of state. The simplest one is PV is equal to RT, the ideal gas equation. Van der Waals, Redlich-Kwong, and a couple others. But they try to get a relationship between, let's say, pressure and temperature and volume. Those are very common. We had some mathematical backbone that's used a lot in this chapter. A review of some calculus, chain rule, differentiation, partial differentiation. And then we started to build property relations. We got the Clapeyron equation and then the Clausius-Clapeyron equation, helping us get the change in enthalpy from pressure, temperature, and volume measurements for a phase change, HFG. Okay, and then also think about the pressure and the volume and the temperature are relatively easy. Conceptually in your mind, you think, yeah, I could measure those and report them in a table. But measuring entropy, internal energy, and enthalpy are harder. They're the hard ones. And so coming up with changes in entropy, changes in internal energy, and changes in enthalpy is the focus of a lot of this chapter, although it's pretty mathematically intense. Other relationships, the volume expansivity and isothermal compressibility, some other properties that we'll talk about hopefully today. The bottom line is how to construct the tables of properties that you take almost for granted. That's what the backbone. And then there's some other departure chart. It's analogous to the compressibility chart. Remember Z? So you said, well, it doesn't behave perfectly as an ideal gas, so we'll have a compressibility factor Z, and that Z will be a function of the actual pressure to the critical pressure and the actual temperature to the critical point temperature. In general, then you had a way of modifying the ideal gas law with this compressibility factor. Likewise, we have charts to get enthalpy and entropy departure from ideal gas behavior. That'll wrap up our chapter. Let's take a look at this problem. It says evaluate the partial derivative. So how does entropy with respect to specific volume change at constant temperature for the substance propane at a fixed temperature and a fixed specific volume? Well, a couple ways to do this. One is you look at going into the tables and you just say, well, can I find where this is in the table? And you can, and what you do is you look it up and you find that it's in a certain pressure block. Oops, I didn't write that pressure block data down. Oops. Well, I'll have to look it up in the back here real fast. So if you have your tables, you can follow along. Just go to the pressure, propane, then find the pressure block where 20 degrees C and that value for specific volume is matched. That's at a pressure of 6 bar. And so at a pressure of 6 bar, you can maybe repeat V was let's do this. Temperature, here, do it like this. Pressure, temperature, specific volume, entropy. So the pressure was in bar, and it was 6 bar. And the temperature in degrees C, it was 20 degrees C. The specific volume in meters cubed per kilogram, 0.08187. And the entropy corresponding is 1.815 kilojoules per kilogram Kelvin. Okay? And now what you want to do is you want to get how does S change as I change specific volume along a line of constant temperature. True? And so you think, okay, well, I have this value for V, 0.08187, and I have this value for S, 1.815, And I need to get a value maybe a little below it and a little above it, but I need to stay at the same temperature of 20 degrees C. Well, go to another pressure block. Maybe go to the pressure block of 5 bar, 20 degrees C, and so it's the same temperature, 20 degrees C. We look up the specific volume, 0.1005, and the entropy, 1.858. Likewise, maybe we go to the pressure block above, 7.0, 20 degrees C. Look up the specific volume, 0.06847 for the propane and 1.776. So you just picked off two values like that. Okay? How do I approximate the derivative? Any suggestions?
Changing S or changing
Yeah. You could do it from just using these 2 points right here. True? So it's how the change in S divided by the change in V. Okay, that might give you the slope of that line. So the partial of S with respect to V at constant T would be this, you want to call this point 2 and this point 1. So it'd be S2 minus S1 divided by V2 minus V1, true? Where those points are all at the same temperature. You could also call this point 3, and maybe you say it's also approximately equal to, because they're going to get a slightly different answer, S3 minus S2 divided by V3 minus V2. Both of those will work. What I think I had was, if I did it with this set, I got the value 2.308. With this set, 2.91. What do you want to do? I weighted them, and with a little review of numerical methods, you get the value 2.658. What are the units on that? Well, it's the units of the change in entropy, kilojoules per kilogram Kelvin, per the change in specific volume, meters cubed per kilogram. So it does reduce a little bit. So you have kilojoules per Kelvin meter cubed. You can even reduce those units even further, true, 2.658. What is a kilojoule? Is it a kilopascal meter cubed? Yeah, so it'd be a kilopascal per Kelvin. So that's a good numerical approximation. What's another way of doing this? One other way of doing it would be trying to use one of the relationships that we covered in the text, which was the Maxwell relationship, that the rate of change of S with respect to V holding T constant is equal to the rate of change of P with respect to T holding V constant. That's one of the Maxwell relations. So maybe it's easier to calculate this derivative. And if it is, then that's equal to the other derivative that you're looking for, the derivative of interest. Another way to do it is to say, let's go ahead and use the Redlich-Kwong equation of state, which is given by P is equal to R bar T divided by V bar minus B minus A divided by V bar times V bar plus B times T to the 1/2. Great. Okay. Where do I get those constants A and B? They're in the back of the textbook in a table, A24. So you can look up for propane. That's our substance of interest, propane. In table A24, the coefficient A in the Redlich-Kwong equation is equal to 182.23. Funny units here. Bar I'm going to run out of room, aren't I? Let me try and write it down here. A is equal to 182.23 in units of bar, that's pressure, meters cubed per kilomole, quantity squared, times Kelvin to the 1/2 power. That may be one of the most unique grouping of coefficients or units for any parameter so far. True? I mean, it just is a mix of parameters. And then the coefficient B is equal to 0.06242 units of meters cubed per kilomole. All right. So what do we do here is you take this equation and you see if you can't analytically calculate the derivative of pressure with respect to temperature holding specific volume constant. So just take a look at the Redlich-Kwong equation and calculate that derivative. So you get R bar divided by V bar minus B, true, for the first part. And then what about the second part? I have to differentiate it with respect to temperature. And there's temperature right down here, true? So you get A, V bar plus B, true. Now you have to differentiate that. So you get a minus 1/2, true, times T to the negative 3/2, or 1 over T to the 3/2. Did you follow that differentiation? Good. And then it's plug and chug. So you plug in the value of B. You plug in the value of A. V bar, just a little bit of work. V bar related to V divided by the molar mass, true? Or is it multiplied by the molar mass? Which one is it? V times the molar mass or divided by the molar mass? Which one? So chase your units. What are the units on big M, molar mass? Kilograms per kilomole. And then, so V is meters cubed per kilogram. So V bar will give meters cubed per kilomole. This looks right. Okay. We have to look up the molar mass of propane, which is 44.09 kilograms per kilomole. And then you have all of the V bars. Okay. What about the R bar? What is that? 8.314. True. But watch your units because 8.314 kilojoules per kilomole Kelvin. And then the temperature, it's evaluated at 20 degrees C, so the temperature is 273 plus 20, 293 Kelvin. True? When you do that, you crunch away, making sure to watch out for units. A bar is 100 kilopascal, and you'll get that this derivative dp dt at constant V using the Redlich-Kwong equation of state is equal to, let me deal with this here, is equal to 2.481 units kilopascal per Kelvin. So how do they compare? It's about 8% difference. It's 8% lower value from the values in the tables. I wouldn't recommend such a coarse equation of state. This is just an approximation, the Redlich-Kwong, as well as the approximation to the numerical derivative. So, but it gives you a sense of how things are put together in this chapter. True? All right. I'm sorry? Yeah, they came out of the table A20 something, A24 for this equation of state for propane. You change propane to different gas, the A and the B constants in that equation of state change. Now let's take a look at the equation to calculate the change in only enthalpy for a single phase region. Here's the equation. We'll derive it in a second, but let's take a look at this equation. It says if I want to calculate the change in enthalpy from a state 1 to state 2, it's the integral of C sub p dt plus the integral of 1 to 2 of something dp. So something integrated with respect to temperature, something with respect to pressure. How did this equation come about? Well, we can derive it. Here's the derivation. It's in the textbook, so I give you kind of a Cliff Notes overview of it. But it gives you a sense of how this whole chapter is put together. We start with S is equal to assumed to be a function of temperature and pressure. Then you can get through chain rule. ds excuse me, ds is equal to the partial of S with respect to T, holding pressure constant dt plus blah, blah, blah. You use Maxwell's equation to go and change out this part right here, one of Maxwell's relationships. So there you go. Now we have ds is equal to a function. Stop. Do that for h. H is assumed to be a function of temperature and pressure. Chain rule, dH is equal to all that. And then by definition, what is specific heat, constant pressure, C sub P? Is that by definition the partial of H with respect to temperature holding pressure constant? It is. Where did we see that before? All the way back at chapter 3. Go back and take a look at specific heats in chapter 3 of this textbook. So we substitute there. We also can recall that dH is equal to TdS plus VdP. Where did that come from? When we were introduced to entropy in chapter 6 of the textbook. So you take and replace dH. So you use this equation for dH and substitute into the left-hand side. And then on the right-hand side of the equation, substitute for ds in the TdS right here. And then boom, you get this long. So this was all brought in from dH. You have T times ds plus VdP. Doesn't look like we're getting anywhere, but you regroup the terms. So everything times dP is equal to everything times dt. So you group your terms, and then you say to yourself, if this relationship will work if dt is equal to 0 and dp is not equal to 0. If that's true, if that's going to work under that case, then this whole right-hand side is 0. The left-hand side is the product of two things. One of them, dp, is not 0, but the product has to be 0. Hence, everything inside the bracket has to be equal to 0. So you rearrange that to get this partial of h with respect to p holding t constants equal to, boom. That was a lot of work to get to this result, wasn't it? You substitute that into the dH relationship, and you get this is the relationship that we wanted. So what we set out to show is shown. I didn't say that derivation was pretty, was it? It's pretty tricky. You don't have to do a derivation on the exam, but at least you see how the derivation is done. Here's a question. Take this equation, the same equation, and apply it for an ideal gas, assuming constant specific heats. So what do we know? If we say it's an ideal gas, then PV is equal to RT. True? If it's an ideal gas, then V is equal to RT over P. And now I want to calculate the derivative of V with respect to temperature holding pressure constant. So what do we get? R over P. So right here, substitute R over P. And right here, substitute RT over P. True? And when you do that, what you'll get minus T in bracket like that. Guess what that is equal to? What is it equal to? 0. True? So what we find is for an ideal gas, H2 minus H1 is equal to the integral of C sub P dt from 1 to 2. And if you assume constant specific heats, you get that it's equal to C sub P T2 minus T1. Well, it's somewhat comforting to know that this long, elaborate, doesn't make much sense when you look at it equation, simplifies to something that you're very familiar with. And that's the change in the enthalpy. For variable specific heats, it's just a function of temperature only. And if it's constant specific heats, then it's just C sub P dt. Now let's move into, there's a whole lot more of that where it came from, true? This chapter is full of it, okay? Try to get a grasp of what's it all mean. What it all means is that there's a lot of work that goes behind getting the tables of thermodynamic properties, as well as the software to run accurately, to give you property evaluations under a lot of conditions. Two-phase, single phase, liquid, solid, vapor, all of that, these equations work. But here's another property. It's known as the coefficient of volume expansion or volume expansivity. The symbol for the volume expansivity is equal to beta. And it's by definition 1 over the specific volume, the rate of change of specific volume with respect to temperature holding pressure constant. And this property you will see in natural convection. When you get into a whole class called heat transfer, you'll study forced convection and natural convection. Forced is when you have a pump or a fan and it's moving it across a surface. Natural convection is you just have nothing to make it want to move, but if you have a hot region and a cold region, let's say I have a room and it has a hot side and a cold side, the hot air will try to buoy up in a gravitational field. Look, give me the symbol for the gravitational field. And the cold will sink. Hot air rises, cold air sinks. And so the strength of the natural convection will be proportional to beta. It'll be a property that's used in a Rayleigh number or Grashof number to characterize the strength of natural convection. So this is the property, beta. It's 1 over rho, 1 over the specific volume times the rate of change of specific volume with respect to temperature holding pressure constant. Some books will show you that it's equal to minus 1 over rho, the partial of rho, with respect to temperature holding pressure constant. Which one's accurate? They look similar, but there's a negative sign on that second one, isn't there? Guess what? They're consistent, but how do you show that they're consistent? Well, let's do this. What is the relationship between specific volume and mass density? Is that it? Is that the relationship? So you can start with one side or the other. Beta is equal to 1 over V, 1 over V, the partial V with respect to T holding P constant. Okay. Substitute, you get that this is now rho, isn't it? But I have to calculate the rate of change of 1 over rho with respect to temperature holding pressure constant. True? So there's the rub. What is the derivative with respect to temperature of 1 over rho? This is one of those where you just have to remember. So you recall something from calculus. So if I have f as a function of x, right, and I want to differentiate 1 over f with respect to x. How do I do that? Is it the same as the differentiation of f to the minus 1 dx? So is it negative df, negative f minus 2 df dx? How many people like that? Right? So in this case, if we apply that, it's rho times a negative rho to the negative 2 times the partial derivative of rho with respect to temperature holding pressure constant. If I did that right. So you get the negative 1 over rho, partial rho with respect to temperature holding pressure constant. It's what we set out to show is shown. They're consistent. But you do need that negative sign. It's not a typo when you go from specific volume to mass density. Develop an expression for the volume expansivity beta, given by the definition here, for a true ideal gas. Okay, so the ideal gas is PV is equal to RT, or V is equal to RT over P. And it looks like I need to differentiate V with respect to T holding pressure constant. When we do that, we get R over P. So let's substitute in. So this first term is 1 over V, which is RT over P, times the second term, which is R over P. The R's cancel, the P's cancel, and we're left with a very simple relationship that beta is equal to 1 over T. Okay? If somebody says calculate the volume expansivity for air, which behaves often as an ideal gas, at 20 degrees C, some students will put beta is equal to 1 over 20 or 0.05, and they'll be wrong. Why would they be wrong? I need absolute temperature scale. Why do we need absolute temperature scale? Because we started with this equation, and what is the T in that equation? Has to be in Kelvin, absolute temperature scale. So if they said 20 degrees C, it's 1 over 293 Kelvin. Notice the units on this are inverse Kelvin. That's the units of beta, inverse Kelvin. Here's another one. Sometimes I'll see it. They'll say, its temperature is 0 degrees C, calculate beta. The student will go, oh, it's 1 over infinity. No, it's not. It's not, okay? So you know it's not. You have to add the 273, and then it'll work. Now, once you've done it for an ideal gas, you can now do it for a gas obeying this equation, which is P times V minus B equal to RT. So that coefficient B could change if it's this ideal gas or that ideal gas, oxygen or nitrogen or argon. But let's go ahead and try to do the same thing, calculate beta analytically for this gas obeying this equation of state. Well, rearrange it such that you get V is equal to B plus RT over P. Did I do that right? And then now we get the partial of V with respect to T holding pressure constant. And B is a constant, so that doesn't come into play. And we're left with R over P. So in this case, beta is equal to 1 over V, 1 over B, write it out, B plus RT over P times R over P. And you could simplify it a little bit, but it's really not going to simplify much. It's going to be BP plus RT, something like that. That's beta. Sometimes when I teach heat transfer, we find that students really get to the notion of how to do natural convection calculations in air, and then beta is 1 over T, 1 over T, 1 over T. And then I give them a natural convection problem in liquid water. Now, it's not as strong as in air, but warm liquid water typically expands, cold liquid water typically, and you can get a natural convection current in liquid water, okay, where you have a warm region and a cool region. But don't use 1 over T for liquid water, right? What you have to do is you don't have a nice simple expression for the volume expansivity of liquid water. You have to go to tables. But one of the things about liquid water is it's very unique. I went off the website, just grabbed this plot. Notice that the mass density, rho, as a function of temperature for liquid water, pure liquid water, at 1 atm, and it goes up until it reaches 1 gram per cc, 1,000 kilograms per cubic meter. And then it goes down, and this special temperature is 4 degrees C. There's a few numbers we should remember. 4 degrees C is a very special temperature for pure liquid water. It's where we have the highest mass density. Okay? Our intuition says as you warm it up, so temperature goes up and up and up, then it expands. But water does something funny when it freezes, when it gets really cold, close to 0 degrees C, and then even when it gets into freezing, what does it do upon freezing? It expands. It expands. The mass density goes down, and it expands. And so you have to watch out for freezing water. Okay, so at 4 you get the maximum. So let me ask this: what is beta when the temperature is greater than 4 degrees C for liquid water? Is it equal to is it positive or is it negative? You know, is it negative meaning it's less than 0? Is it maybe equal to 0, or is it greater than 0? Which one is this? Is beta? And then also, what is beta at 4 degrees C? Is it less than 0, equal to 0, greater than 0? And then what is beta for liquid water between 0 and 1? I'm not going to consider natural convection in solid ice, right? But you can have buoyancy in cold water right before it freezes between 0 and 4 degrees C. So the temperature less than 4 degrees C. Which is it? Positive, negative, equal to 0? Right, okay. So first of all, this one is 0, true? The slope is 0, right? And then here you have a positive slope. So the rate of change of density with respect to temperature is positive in this region, right? We put 1 over rho with a minus sign, and doesn't that give us beta? So what is beta? How it expands on increasing temperature? This will be negative here, right? And then this will be positive when it's greater, true? So it's kind of funny about liquid water. Most liquids don't do that. They just have a positive volume expansion coefficient. Well, the next property is known as the volume metric compressibility. What is the definition of the volumetric compressibility coefficient? Let me find it here. It's given the symbol kappa, and it's equal to a minus 1 over the specific volume times the rate of change of specific volume with respect to pressure holding temperature constant. Holding temperature constant. So that's another property, isothermal compressibility. All right. What is the isothermal compressibility for ideal gas? How would you calculate it? Well, go back. PV is equal to RT. And then V is equal to RT over P. I see I need to take the derivative of V with respect to P holding temperature constant. What is that derivative then equal to? Negative RT over P squared. Is that true? And then substitute in, so we have kappa is equal to negative 1 over V RT over P times negative RT over P squared. See what cancels RTs? The signs cancel, and one of the pressures cancels, so kappa, 1 over pressure, only for ideal gas. So there's a coefficient, isothermal compressibility. It's how does it change as I just changed temperature without changing pressure. Well, I just did this problem, half of it. Develop an expression for the isothermal compressibility for an ideal gas. Did that. What did we find? Kappa is equal to 1 over P. True. And then what happens if it obeys that equation? I think we've done enough of that, right? You can handle that if you need to. So let me skip it. How about the isentropic compressibility? Well, the isotropic compressibility alpha is defined as negative 1 over the specific volume times how the volume changes as I change pressure holding S constant, isentropic. Isentropic. True? All right. Now, this is a tough one. How about for an ideal gas? We know for an ideal gas, PV is equal to RT at all times. True? Okay. But I would like to take this derivative. I'd like to take that derivative. How am I going to take that derivative? You have any suggestions how to calculate that derivative? And the key is I have to go beyond this equation. I can't use only that equation. I have to find a relationship between pressure and volume where one other property is constant. What is that other property? S. Do I know of any equations where I have pressure and volume are related for an ideal gas and it's isentropic? This equation, P V to the K is equal to a constant. You know, first time students see this equation, oh, it's great. I'll apply it to steam in the two-phase region. I'll apply it to water and liquid. No. This applies only for an ideal gas, and only S is equal to a constant. Isentropic process, true? So it's embedded in there. So if I want to calculate the derivative, I have to rearrange this. How can I rearrange it? Put constant over pressure is equal to V to the K, true? Now the next step, what's the next step? V is equal to a constant over pressure to the 1 over K? Or did I butcher any rules of calculus? Do you like that? What was K again for air? Roughly 1.4, 1.4, right? So now that I have that, can I calculate the rate of change of V with respect to pressure? And I know that S is constant, so I'm going to have the C to the 1 over K as a constant. Forget about that. And I'll have P to the minus 1 over K. Let me rewrite it. Maybe that's what I need to do. C to the 1 over K. P to the minus 1 over K. True? Okay, you differentiate that, and the constant 1 over K is sitting there. So what do we get? P to the minus 1 over K minus 1? Yeah, you like that? How many people like that? Right? Does that look okay? Is that what you got? Very good. Now you can rearrange this a little bit, right? Because 1 is K over K, you get a common denominator. And so if you wanted to, you could rearrange it, but let's leave it there for a minute. Let's come over here. So alpha is equal to minus 1 over V. Okay, well, what do I do for V? Is V always, here's a question for you. For this V right here, should I substitute RT over P? Or should I substitute 1 over V? V is equal to P over C to the 1 over K. See what I'm doing? I'm either going to here or I'm going to here. Well, V is equal to RT over P. There. What should I just want to deal with this 1 over V first. The first one. Okay, we have a vote for the first one. Others? You like that one? You like that one? He likes the bottom one. Okay. We got a bottom, so we're going to go for a runoff. How about this? Could both be correct? Probably not. Probably not. It would be pretty far out on a limb that they would both be correct, right? So let me ask you this. This derivative was forced to have what held constant? Entropy. This 1 over V, is that forced to have entropy constant? That's the biggest clue I can give you. So, which one do you like? First one. Very good. All right? But now when we calculate that derivative and substitute, we're going to have C to the 1 over K minus 1 over K times P to the 1 minus 1 over K, P to the minus 1. Okay, fine. That looks like a pretty garbled up mess. But this and this cancel, true? And then the minus sign and the minus sign go away. And we do have some more work ahead of us, but we're going to have, if I combine this C right here with that P right there, right? What do I get? I get C over P to the 1 minus. Can I replace that? This right is V equal to C over P to the 1 over K. That's what I'm going to use right there, true? So alpha is equal to V over K R T. Okay? Did I botch it or does that look okay? Looks fine? And then the other one is somebody says, I think I can simplify this term right here. True? What is V divided by RT? 1 over P? So alpha is equal to 1 over Kp. For what? An ideal gas. Isentropic compressibility of an ideal gas. Okay? All right. Well, with that, I think I'll go ahead and stop because I don't have enough time to get into Joule-Thomson. We'll get into Joule-Thomson next time. Thank you.